At Case Western. We have three papers in this session. Two of them are research track. One is a journal track paper. The first speaker is Igor. He's going to talk about back semantics of DL light with functionality axioms.
All right. Thank you for the introduction, and I hope everyone who wants to can hear me properly. Is it okay? Yes? Very well. And yes, my name is Yegor, and I'm presenting a work with a bunch of people from Oxford, or people who used to be in Oxford, like John Luca, Babis, or Harlampos, Mark, Bernardo, and Ian. And this is a work about back semantics of DL light with functionality axioms. So let me start with a little bit of motivation, and in particular with a brief introduction to OBDA, ontology-based data access. Actually, like, who knows what it is? Okay, not everyone. Okay, let's very quickly explain what it is. So, let's say we have some database, then we have some mappings which send our database to some A box, which is usually just virtual, so it's not materialized. And then on top of this A box, we have also some ontology, meaning some T box, in some kind of description logic, maybe DL light, or its instantiation like OWL or something like this. And then a user poses queries over the vocabulary of the ontology, meaning that over the T box and A box. But since the A box is not usually materialized, we are interested to rewrite these queries, to evaluate them over the original database rather than over the virtual A box and T box. Well, but this materialization step is usually considered as simple, and that's why it's usually in theory considered that, okay, we have this A box materialization of the database with the mappings, and what we are interested in is to rewrite queries so that they work just over the A box without the axioms in the T box. And this is called the rewriting. Okay, so, but let's look at an example. And we have some database which consists of just one relation, R, about some bands and albums and the years. And then we have a mapping which just uses some maybe SQL query which just projects to the bname attribute. And we have our materialized, in this case it's materialized, but our A box over band concept, band unary relation. Right? So this is like pretty much standard query. But here you may notice that actually SQL works a little bit not as in this example, because the query which underlies our mapping is a SQL query, and it preserves multiplicities, right? So if you know SQL queries, they may give the same answer not just once but several times. And in this case, of course, if we just project on the bname attribute, we will have Pink Floyd twice, right? This is usually considered as a minor thing, and we just ignore this thing, and our A box is a set of facts, as in this example. But sometimes multiplicities matter. And this happens when we have, for example, aggregate queries, when our queries over the ontology is actually not just a simple, maybe conjunctive query, but something where we need to take care about multiplicities. Right? And this is actually quite an important situation when we really want to do something like analytical queries. Well, all of us sometimes use aggregate queries when we want to count something. And so basically this mismatch is usually hidden under the carpet, but it is important. And we want to study what actually happens if we want to preserve multiplicities. Okay, so roughly speaking, let's start with some overview. I'll continue with an overview what we want to do. So we want to consider query answering over ontologies, where ontologies are expressed in a popular ontology language, DLite F, meaning that it is a simple ontology language, but it uses some functionality axioms. We will see a couple of examples. But we want to take care about multiplicities. In this case, our A box, our set of facts, is now not just a set, but a bag of assertions. Also interpretations, logical interpretations, they assign bags rather than sets to concepts and roles. And we will introduce two variants of semantics for this extension of description logics, and study the properties. In particular, we will study query answering, which takes care about multiplicities, and we will also see when we can do rewriting as I just described, when we can rewrite over the A box preserving multiplicities. In this case, we will rewrite to SQL, to the language which really cares about multiplicities. Okay, so let's briefly look at the existing language, DLite F. And this is an ontology language. We start with atomic concepts and roles, unary and binary relations. Then we construct more complex concepts and roles, which are either like as on the slide. I hope more or less everyone's seen something like this in their lives. Then we have T-boxes, which are sets of inclusions or disjointness axioms or functionality axioms. Like the last one is probably the most important for us in this work, because this is precisely what differs this work from the previous works. And then A box is just a set of facts over this concept and role names. And then an ontology is a pair of T-box axioms and A box assertions. Well, the semantics, I don't want to stop on it. It's pretty much straightforward. We have interpretations of atomic concepts, and then they propagate, and then they either hold or doesn't hold, satisfy or doesn't satisfy A box and T box assertions and axioms. Right. Then we have conjunctive query answering. These are just standard conjunctions in logical form, unions of conjunctive queries. And then we can talk about certain answers of conjunctive queries over ontologies. This means that a query for some tuple holds in the ontology if it holds in all the logical models of the T box and the A box. This is pretty much standard. And then a rewriting of a query over a T box is another query, either in the same language as a CQ or UCQ, or maybe in some more expressive language. But the important property is that we can evaluate this new query just over the A box, just over the facts we have, kind of rewriting out the T box. Importantly, this rewriting, it depends only on the T box. So it should work for all the A boxes, for all the data, kind of independently. Right? So I hope more or less, if you are here, you may know what I'm talking about. Right. But now, well, we want to generalize this picture to bags. Fine. So what is a bag? Now we care about multiplicities, right? So we assign maybe to some facts to some assertions in the A box. We may assign some multiplicities. We may assign multiplicities to statements in the interpretation. But just in general, a bag or a multiset is a function from some object to some numbers. Then we can generalize sub-bag relation, generalize subset relation to bags. Then we have some operations like union, max union, arithmetic union, intersection. All this is intuitively pretty much straightforward. Then duplicate elimination and so on. And just as an example, we may have a bag A box, which is actually now a bag of assertions rather than a set of assertions. Right. So, in the case without functionality axioms, this was studied before. And already we have DLLite core, the back version of DLLite core, meaning the same language but without functionality axioms. And this was introduced in previous work. Here, as I said, the A box may have multiplicities, but the T box may have is the same as it was before. Then we can say what is the semantics for the interpretation pretty much in a straightforward way. The only question is how to interpret exists are concept, meaning that we want to project to just one argument of a role. But here we take back projection. So we basically sum up all the multiplicities when we basically project the second argument, as it is written on the slide. Then we can say that an interpretation satisfies axioms, okay, inclusion, straightforward, disjointness, again, straightforward. Here, the subset relation and intersection are for bags, as on the previous slide. And then we can say that an interpretation satisfies a bag A box if the multiplicity in the interpretation is greater than the multiplicity in the A box. Okay, but now what to do with the functionality axioms? So just as a simple example, maybe we have this inclusion, exists P implies exists S, but S is functional. And maybe in the A box we have two copies of P for O, two outcoming P relations. So we need somehow to satisfy it, we need two outcoming S roles, but S is functional. So an obvious idea would be, okay, let's add one more S from O to C. So that's somehow, at least intuitively trying to preserve functionality axiom, right? So saying that there exists just one C such that O is connected to C, maybe with several copies, but still just one. And we have a choice. Is this interpretation does this interpretation satisfy the T box and A box or not? If we follow standard approach of SQL and saying that functionality axioms are actually key constraints, primary key constraints, then we have to say that this interpretation does not satisfy our knowledge base, and moreover, of course, we just don't have any model and we are not satisfiable at all. And this is one way to deal with this functionality axiom. Another way is saying, okay, it's fine, and we have this satisfaction. This situation is okay. All right, so we have two semantics, either SQL or MR semantics for bag interpretation. And pretty much the rest is as it was before. So, now we study this ontology language. For satisfiability, apparently, well, we have two semantics, two languages. For satisfiability, we have this first semantics, SQL semantics, is pretty much the same for satisfiability as the back version of it, like theorem 2.1. Well, of course, proposition 1 is just the corollary of the definitions. But for satisfiability of the second semantics, we have that. Sorry, I said wrong. For the second semantics, it's just the standard set semantics satisfiability, but for SQL semantics is different. And we have that the complexity is slightly different because of these things. Okay, now for query answering, well, I don't have much time, but back semantics of query answering is pretty much as in SQL. For example, in this we have 7 copies of the query, so the answer is 7. And we can define certain answers in a kind of straightforward way. The only important thing that we care about, well, we have many models, right? And we want to say what is the certain answer for many models of a query. And here we commit to this kind of idea that the certain answer is the minimum over all possible models, the minimum number of answers in all possible models. And this is our semantics of query answering. And then, okay, we have this decision problem. Is the number of answers to this query is more than a specific number we ask about, so we need to turn it to a decision problem, and this is a natural way to do it. And we start to study it. Unfortunately, we already know that we have bad complexity, CoNP hardness, even for the case without functionality axioms, and this, of course, propagates for the both of our semantics. But we also know that if we restrict our queries a little bit and talk about rooted queries, and these are very mild restriction where we consider the case when we each connected component, oh well, forget about connected components, just think that every query has an answer variable, non-Boolean. Then we actually have this like good results, like rewritability and tractability of query answering, even, okay, without functionality axioms, but also we can extend these results to SQL semantics in a straightforward way. We have rewritability and we have TC0 complexity for query answering. However, for the second semantics, these results don't propagate that nicely because we can show that even for rooted queries, for these restricted queries, we have log space hardness in data complexity, and this implies that we don't have rewritability. However, if we restrict our interaction of functionality axioms with in the T-box, like globally, if we don't have any cycles through functional roles in the T-box, then we can recover both rewritability and good complexity of query answering. Right, so let's sum up what we have. We studied an extension of query answering over ontologies with back semantics, and particularly ontologies with functional axioms. This is motivated by aggregation. Then we introduced two semantics for functional axioms, SQL and MR semantics. Both of them have their own pros and cons. Overall, we know that query answering is hard, but if we impose some small restrictions, then we become actually tractable and rewritable. For the future work, of course, we want to consider more ontology languages, such as Datalog plus minus, for example, or OWL2RL. Also, we want to know the same for other query languages, so not just conjunctive queries over like our user queries, but also maybe Sparkle. And of course, we are interested in implementing these things, and so to see how it works in real life. Okay, that's it. Thank you.
Any questions?
So, thank you for presentation. Just a question: can we compare back semantics with standard semantics? I mean that if we take ontology and we check it if a consistency under standard semantics. For example, it is consistent.
Yeah, okay.
So now we check the same ontology under back semantics. So it is consistent or not?
Yeah, okay. Sorry if I rushed through it, because it was I wanted to focus on the setting rather than on the results. So, yes, we can compare, and this is reflected in, say, for satisfiability, where it is. Yes, of course, and actually this is the results. So for one of our semantics, for MR semantics, satisfiability is the same as in the set semantics, under set semantics. So if we can satisfy under back semantics, then we can satisfy under set semantics, and other way around. For the other semantics, for SQL semantics, just one direction holds. So satisfiability under SQL implies satisfiability under back semantics. Of course, when I'm saying this, I talk about like when I don't care about duplicates in my A box, right? So
Standard semantic is stronger than back semantic or
say again?
The standard semantic is stronger than back semantic or not?
Okay, to compare them, we need to match these things, right? Because if we have multiplicities in the A box. If we forget about multiplicities in the A box, then we can compare them, and pretty much one of our semantics will be precisely the same in terms of satisfiability. The other semantics will be stronger. Yes, you are right. But for query answering, it becomes like much more difficult.
That's because if you can start with set semantics, but then generate multiplicities because of the functionality.
Well, yeah, of course, if we start in the set semantics in the A box, then
Start with no multiplicities, everything appears one.
in the data or in the A box,
In the A box, yes.
I don't think how can you generate?
Your functionality, the second semantics, you might have
Yeah, you are right. It is possible. Yes,
you might generate.
multiplicities. Yes, but it doesn't affect satisfiability. It affects query answering and query rewriting.
Questions? Okay, then let's thank the speaker. We have the third speaker again. Okay. So our next speaker is Abhinod, and
Okay, yes.
and he's going to talk about optimizing Horn-Schick reasoning for ontology-based data access.
Oh, just a second, I think. Should. Is it? No? Okay. Too close? Okay. It's okay, perfect. So. Oh, no, I'm fine. I figured it out. Oh, now fine? Okay. Okay, so thank you for the introduction. So the work I'm presenting here today is in line of optimization of Horn-Schick description logic with the aim of making it more suitable for ontology-based data access. Our motivation for doing this is that state-of-the-art OBDA systems are based on DL-Lite, and while this is for a very good reason, because as query answering is a key service in OBDA, the nice computational features that DL-Lite has with respect to this problem makes it a natural candidate. But in the other side, there are many application domains in which the DL-Lite expressiveness is simply not enough. So we focus here in Horn-Schick, which is a quite expressive description logic that actually contains all the constructors, the DL-Lite and even EL, and adds on top of it transitive roles and role restrictions. And we aim to optimize this for OBDA setting. So when it comes to query answering, the most well-known and actually the only algorithm that is complete for all features of Horn-Schick is the one designed by, known to us at least, is the one designed by Eiter et al. This algorithm is also implemented in a system called Clipper. It relies on building the canonical model or the universal model in order to facilitate query answering, and it does this in 3 steps. In the first step, it employs a specially tailored calculus to infer new axioms that may be needed to build the universal model. In the second step, then it basically closes the A-box under all the derived axioms but the existential ones, and in the end, it employs, it basically runs a chase procedure with existential axioms obtained in the step 1. However, this algorithm has a problem. It's quite expensive, and it's not just hypothetically worst case exponential maybe, but it performs quite badly in for a lot of realistic ontologies. And this is mainly because it's A-box independent. We will illustrate this with a simple example. Consider this snippet of an ontology of anti-money laundering ontology, which basically has the purpose of tracking suspicious activities in banking accounts, where the first axiom basically says that a monitored account has to be flagged. The second axiom says an individual account that is also monitored has to have the flag, yellow flag, and so on. If we saturate this with the existing calculus, a rule known as, for example, in this case, the for-all rule becomes applicable, which basically states that for each existential axiom, this pointer doesn't work. So for each existential axiom that has a matching role with some axiom that has universals on the right side, it derives an axiom which basically foresees that in some A-box there might exist some individual that is a monitored account and individual account. Therefore, it has to have some flag that is a yellow flag. So far, so good, but if we continue saturating this T-box with a given calculus, we see that we get an exponential blow-up, actually, on the number of axioms, basically in the number of universal axioms on the right-hand side that combine with the existential axiom on the top. Basically, we have 2 to the power of 3 minus 1. And if we inspect them closely, we see that most of them are not needed because we will never have an A-box that is together an individual account and a small business account or etc. We expect these to be disjoint. However, due to completeness and naivety of the calculus, these have to be considered and added there. So how do we go about addressing this problem? Well, we try to use some information about the structure of the A-boxes or relevant A-boxes. And this is very natural for the OBDA setting where A-boxes are actually generated via mappings, and we can predict their structure. We define, we use actually this, So we use the notion of A-box types to capture the concept assertions that an individual might satisfy in some relevant A-box for us, and also its neighborhood, for example, incoming and outgoing roles. And we use this to derive activators, which are a key component in optimizing the calculus. And what activators in our case have to cover, they have to cover all the concept assertions, and moreover, we require them to cover all the potential concepts that might be propagated from the neighborhood of of the A-box type. We call these also over-approximated A-box types. And for an A-box, we say that an A-box is covered by a set of activators if for each of the individuals that occurs in the A-box, we can find some activator that contains the over-approximated A-box type. So now, assuming that we have a set of activators that cover all the relevant A-boxes that can happen in practice, let's assume that we have them, we can optimize the calculus by adding these side conditions. Side conditions, which basically check if the left-hand side of the axiom that we want to derive is contained in one of the activators. If it is there, then it's derived. And moreover, we of course take care that the set of activators is actually closed under deterministic rules, and we also have to add them on the way of the derivation process. The last rule here is just for housekeeping, basically removing redundant activators. Okay, but now how do we get these activators that can cover any relevant A-box? Well, in OBDA is simple. So we use the mapping layer. We focused on a mapping layer that is expressed in R2RML. And basically, a mapping can be seen as a set of mapping assertions that take an expression of the following form, where the left-hand side is basically just a set of database atoms. Right-hand side is a unary or binary predicate. The functional symbol here basically is the IRI function that generates the name of the individual when the mapping is evaluated over some concrete A-box. We make the following assumptions about functional symbols, that for two different tuples, database tuples, and for the same functional symbol, we always get different values. And this is actually also embedded in the R2RML standard. And the second is that for two different functional symbols, we always get different values. We will never get the same values. This is also an assumption that is made in OBDA systems, for example, on top. Now, how do we obtain the activators? Now, consider this simple example of mapping assertions. One simple way would be to treat as an A-box type the set of all the head predicates of mappings that share the same functional symbol. However, this is can be a problem because we can get large A-box types, and if we get very large activators, just think about a singleton activator, for example, that contains all the vocabulary of the ontology, then there is no optimization there. The idea is to have as small activators as possible. So can we do better? And actually we can. We can leverage functional dependencies to define which mappings are conflicting mappings, basically that cannot fire for the same constants. So consider, for example, the relation that occurs here, account details with its attribute ID, type, and size, and the functional the functional dependency that says the type and size depend functionally on the ID. Then it is clear, for example, that the mapping M4 and M5 conflict in the size attribute. So they will never be fired for the same constant in the database. And in the end, when we have all these conflicting mappings, we basically just take the maximal conflict-free set of mappings and use the head predicates in those to generate head predicates that share the same functional symbol to generate the A-box types from where we get the activators. So, and last, some results. We have implemented this, let's say, simple maybe approach, but it yielded quite good results. We implemented it in the Clipper system and compared it with the base version. We used the Oxford ontology repository to test it. After pre-processing the ontologies, we saw that 221 were seen as relevant. We got like 37% increase in the number of the ontologies that we could saturate, basically, with the optimized version versus the 108 with the original one. It goes without saying that in all cases where the unoptimized version succeeded, the optimized version also succeeded. If one takes a closer look in the cases where both of the versions succeeded, one can see, for example, in the graph above, we have plotted the rate of the growth of the saturated T-box with respect to the original T-box. And the red bars are the ones that represent the original calculus or the original Clipper, and while the blue bars, the optimized version. The blue bars are presented here, are plotted on top of the red bars because we always get lower. And if one looks at the graph, sees that most of the axioms that are derived with the original calculus are actually redundant, or not needed for coherencing. Also in the runtimes, the optimized version was nearly always faster. For the gained instances, basically ontologies in which only the optimized version succeeded while the original one failed, we noticed that the rate of growth was in the same range, basically like the other cases. Also, we got good times, running times for these cases. In the end, we also analyzed activators that we can get from OBDA specifications, because the instances that we tested on, we had to get the activators directly from AUCKLAND, because it's very hard to come across many OBDA benchmarks that have mappings and an ontology that is expressed in Hornschik. Actually, there are none. So we analyzed 3 of them with our approach that we described in detail in the paper. And what we noticed is that the number of activators and their size was moderately in the same range as the ones we got directly from the A boxes from testing them against Oxford ontology repository. And in the end, we can claim that this structure-based approach for optimizing the reasoning is promising. We obtained encouraging results. Moreover, one can audit the activators that one gets, and by auditing, the ontology engineer can see that this activator can be broken up because these 2 concepts do not go together, in which case this can improve the performance even further. Moreover, our approach is incremental. It can compute incrementally. For future, we seek to develop more fine-grained algorithms for obtaining the activators, and also to try and validate this approach against more benchmarks. So, thank you.
Thank you. Questions? Okay, so I had one question.
So is that bad, huh?
One question.
Yeah.
So some of the results in your optimization chart, yes. This one, there are a few sort of standouts. For example, about 85, if you have 85 instances, the C-opt seems to be performing worse. Did you look into the cause for that? Why
the cause is because sometimes we have to extract the activators, and sometimes this doesn't pay off. But this doesn't mean that it performs way worse, because this is in a matter of runtime seconds. And this procedure of extracting the activator is not very well engineered, to be honest. So that's why we pay this cost, and sometimes it doesn't pay off. But for a more larger ontologies, it's always. And I didn't have that. I thought that I will be much slower, but we also looked at the distribution of the ontologies, and we have like 25% of the cases were very large ontologies that had over 10,000 axioms, and also very large AUCKLANDs, and it worked well. But this is the reason.
Okay. Thank you. Thanks to the speaker again. The last speaker.
Let's save. Okay. Thank you.
Okay, let's have the last speaker of the session. We have Jerome, I think, for presenting link key candidate extraction with relational concept analysis. This is a journal paper.
I'm very.
Yeah.
Do you need? Okay.
Yeah, I plan to do a demo, but I think it will not be possible. Okay. And then I'm lost. Where is the sign for this? No. No. View. Presentation.
Yeah. Full screen mode.
Full screen mode. They decided to change this. So hello again. Okay, so this is a presentation of a paper that has been published in Discrete Applied Mathematics. So since it may not be read by the audience, the idea was to present it here to give some exposition to this kind of idea. And the goal is to extract link keys, which are devices for linking data, with techniques called relational concept analysis. So, okay. So the point is to extract links. So basically, you have two RDF data sets, and your goal in the end is to have a set of same-as links. Okay, so there are several kind of techniques for achieving this, and we designed one which is made of 3 different steps. The first one is to, so basically it's based on link keys. So link keys is a thing in the middle. I will present just after what it is. But there may be several link key expression, many link key expression across 2 RDF data sets. So first we add an algorithm which extract candidate link keys, which are far less than all the possible link key expressions. And then we add measure to select the most promising one. And this was a result of another previous paper. And once you have link key, you will see that it's very easy to generate the links. And this paper is actually about how to extract the first set of candidates with techniques which are used in data mining, such as formal concept analysis and relational concept analysis that I will explain. So what is a link key? Something like that. Maybe the pointer will be useful, but it doesn't work. Okay. So it is made of a pair of classes, and so the object belonging to this pair of classes may be eventually linked, depending on the value of their properties. So what is in blue is one RDF data set, what is in green is another RDF data set. And such object will be links if for all this pair of properties they share at least one value. And for all these pairs of properties, they have the same value. So if I go for an example, this linky says that if I have the class écrivain and the class writer, any pair of objects of these two classes may be considered the same if they share at least one value between prénom and first name, and if they have exactly the same values for nom and name. And the interpretation that I described corresponds actually to this kind of interpretation globally. This corresponds to the P and the fact that they share at least one value. Is not high enough? I have plenty of my ears already. And this corresponds to the Q properties, and they've got to have the same values. Okay. So, as I said, for extracting the candidates, we use formal concept analysis. So, briefly speaking, formal concept analysis is based on something called formal context. And a formal context is made of three parts. A set of objects. So here in the example, you've got the set of objects, which are animals. A set of Boolean attributes, which are this one. Either they are praying, they are flying, they wear feathers, or they are four-legged. And I, which is called the incidence relation, which corresponds actually to this matrix. Okay. This says that the lion is praying and four-legged. A seagull is flying and wears feathers. An eagle is praying, flying, and wears feathers, etc., etc. So the point of formal concept analysis is you give me your formal context, and I return you my concepts. Okay? And so this is one way of organizing the data of the previous context. And each of these objects are concepts, and they are organized in a lattice. The interpretation of a concept like this one, okay, is actually obtained by inheriting from above everything from the above part, and from below everything from the below part. Okay, it's just like a simple class. So the extent of this concept is seagull and eagle. Okay. And it corresponds to the set of objects which wear feathers and are flying. Okay? So that's relatively intuitive. Okay? And the point of formal concept analysis is that there is a yellow book that has been published 20 years ago, which tells you how, okay, from the formal context, you obtain the concept lattice. It's not far more complicated. It's explained in this slide, but you don't really need to know. If you are a user, you just push the button, it will give you the result. Okay. So, what's the relation with linky candidates? The point of formal concept analysis is basically, if you want to solve your problem, turn it into a formal concept analysis problem. That is, give me the context, formal context, and I will give you the formal lattice. And so here is the point for doing this for simple linkies, that is with only the intersection part. And that's it. I will extend it after that. And so the idea is that we are not trying to find concepts which are sets of objects, but we are trying to find concepts which are equivalent objects, so sets of pairs of objects. Okay? And we are not relying on properties, but we are relying on pairs of properties. So this is, okay, exactly what we will do here. For a set of objects, we will take the product of the extent of the classes that we have. And for the set of properties, then we will take the product of the property that we have. Okay? And the incidence relation will be defined such that a pair of objects is incident to a pair of properties if actually there is a value in common for this pair of property for the pair of objects. Once we have done that, that's done. We have expressed our problem into a formal context, and formal concept analysis is able to solve the problem. Okay? And actually, basically this kind of scheme, not exactly this one, but this kind of scheme can be found also in this yellow book, even it was not about linkies. So let's take a very simple example. We've got here two data sets in RDF of two classes called person on one side and inhabitant on the other side. And they have attributes which are different. At least they belong to a different namespace, so they are different for the algorithm. But they share values. So there are people who are sometimes identified by the same first name, sometimes identified by the same last name. Okay, and they are different. If you take these two data sets and you construct the incidence relation, wow! And I will have to speed up quite a lot. And you construct the incidence relation, this is what you obtain. You've got the pair of objects here and the pair of properties here. And if you run it, you will get this very simple lattice. And so in all the examples, basically what we are looking, the correct result is when you have a Z2 with I2, Z3 with I3, and Z1 with I1. And the correct one is this one, the best one, because it's use equivalent between last name and first name and given. But you would generate on this one more links, okay? These three links plus these two links, which are not correct, which are those who share the same name and last name, but who would be discriminated by the first name, okay? This is very simple, but this works, at least on this very simple example. These were for simple linkies, okay? That is, we don't have two different ways to compare the properties, okay? But actually, we have got two different pairs to compare the properties, so we can extend this to our formal context by quantifying it, okay? So the quantifier here just say that we will interpret the incidence relation in a different way. It will be with the existential quantifier if we were in the previous situation, that is, they share at least one value, and the universal quantifier if they share all their values. Okay? So again, we have found another encoding. We can pass it to formal concept analysis. Here is a slightly more involved example with here some stuff that can help you to make mistakes. For example, here the Jacques is the last name of someone, but it's a given name of someone else. So actually Z4 and I4 are not supposed to match. Okay? So if we take this set, here is the context that we have. So what has changed is that now we have got double the number of pairs of properties because we are quantifying it. And the lattice that we obtain is this one. And the good concept is actually this one, which inherits Z1, I1, Z3, I3, Z2, I2, etc. And this is also, so now it is identified by there exists a common last name and there exists a common first name and given. And by the way, I'm using this for saying that the two pairs of property are satisfied in the intent of this concept. Okay, but this works nicely if you have data type properties, okay, that you will compare easily. But what if you've got sets of objects, okay? The problem when you have dependent concepts is that maybe you will use the owner attribute for identify houses, okay? And in this case, the problem is that how do you decide that when you test if the values are equal, how do you decide this? You need something which tells you that they are the same. So either you already get the same as, but if you don't get them, you can use a link key to interpret them. Okay, so this means that equality will be determined by using a particular link key. And so, of course, you can go ahead, but what I present now works for DAGs, like this. And you can have an algorithm which allows you to determine the link key for this, or determine the set of link key for this, using this set of link key for determining the set of link key for this, and using it for determining the set of link key for this, etc., etc. What are those link key like? Now they are qualified, actually, just what I said. If you have data type property, we do as we did before. If we add object properties, then we will qualify the pair of properties by the actual link key that you use. Okay? And so this simply means that when you decide if there is intersection or equality, for testing the equality of the object on this set or the equality of two objects here, then you will use a particular link key. Okay? So let's do this for another example where you've got the places and houses depending on the person and inhabitants. So you will do exactly like we did before for the inhabitants. Okay? Then you will have the same lattice as before. I will explain the color in the end. Then what you do is that you've got a context which is qualified by the actual concept which were in the previously found lattice. Okay? And you've got this incidence relation, and you can now run your algorithm, and you will obtain this lattice. Okay? So, for example, this one tells you that, this lattice. For example, this one tells you that in D2 tells you that you will unify places when they have the same owner and owned by, and there is a value in it, but it's not really interesting. And you will identify it with the C2 concept. And so when you have the C2 concept, you are actually using the one that I said is correct. You will only identify Z2 with I2, Z3 with I3, Z1 with I1. You can see that above you've got another one, which is using the C1 concept. So then in this one, we'll use other more equivalents than, more same as than before. And then it will return more apartments which are the same. So basically you will have H2A1, H1, A2, H1, A3, and A1. So H1 will be the same as A3 and A2 as well. Okay? And the correct one, in fact, is this one, if I remember well, because, no, the correct one will be this one, H1, A1, H3, A3, etc. Yeah, the correct one will be this one. It uses these two things. That is, the one that I presented you that I say was the correct one, plus it will also use the constraint of the city, because, of course, it's the correct one, so the apartment is in the same city. Okay, so there is something that I did not discuss, which is that the point is that you may have several, so I have to hurry up a lot. Okay. One extra problem that we may have is that you have several objects which are referring to the different attribute to the same class, okay? And what you do with that, because if one wants to use one link key and another wants to use another link key, it may be authorized, but we decided that it's not the case. That is, for any pair of objects, we will identify only one link key. Okay, so this allows you to define family of compatible link key, and this was the color that you can see in the diagram. Okay, now, I explained it here. Okay, the last point is the most interesting thing, and the longer one, is extracting circular link key candidate. But I will try to explain it very quickly because I won't. So circular link key candidates means basically that you may have person which come back to houses, or even person going to houses. Okay, and then in this case, it's not a DAG, so you cannot use the procedure that you have used before. What we will use is another kind of procedure which is called relational concept analysis, which I will not explain. But basically, relational concept analysis starts with formal I will go ahead. Okay. Start with a family of contexts. That is, it will take one context pair, in our case, pairs of classes. Okay, and then it will add relational contexts, which are incidence table between objects, which are depending on relation properties. Okay, and so basically, what does relational concept analysis is that first it starts with a formal context, okay, and run a set of FCA. So it has a concept lattice. Then it uses something which is displayed here, but I won't get into detail, which are called scaling operators. What scaling operators do is that they take the incidence the table of incidence relation, and they will take the context that has been found and create and add them to the formal context. Then it rerun FCA again on this new formal concept. And it does it until there is no change in the data set, so then until closure is reached. And there is a proof that it's always, the closure is always reached. So this is what I presented here. So here is an example, just to give you an idea. And so you've got inhabitants. So it's really funny because you've got people who live somewhere, okay, but actually the apartment is owned by someone else, okay? And everything is circular, just for fun. So the initial formal contexts are very simple. It's even more simple than the one that we had before. And these are the relational contexts, okay? So you see that instead of having properties here, there are pairs of objects, okay? And so this means that for these pairs of apartments, the owner is these pairs of people. I don't know what is making this noise. So we've got everything we need, okay? And is it magic? This is the result, okay? So in fact, I have a demonstration when I can show each of the iteration. And what you see is that you've got two families of compatible keys. This one, which uses C1 as this key. C1 is this one. And C1 is using this C2, which is this one. Okay, so they are compatible. And here C6 is using C4, that you can see here. And C4 is using C6, and they are not compatible. But all these ones are, you cannot determine a pair of link keys which are compatible with this one. Because you see, if you use C8, then if you look at C9, it uses C8, which is there, which will use, I guess, C0. C3, which will use C0, where it is here, and C0 use C9. So it was using C7, which is using C5. So I'm lost. Okay, so this was rather C8. C0, so this was using C3, likely. C3 is using C0. Okay, so I made a mistake. But basically, because I made the owner be different from the people who live there, it has to do the iteration through all this stuff in order to eliminate them. Okay, so yeah, so this is a conclusion. If you are interested, this is everything in this paper. We've got software that works, which are able to deal with this very simple case, but don't scale at all. And we have a more elaborate software that we are currently developing. And there are a number of contributions, and I stop here.
Thank you, Jerome. Let's thank the speaker. Interesting. Any questions? We have maybe one question before we'll have to leave for, I guess, the dinner.